So welcome to lesson 3.2. Now, in their work on social macrodynamics, Andrei Korotayev and his colleagues had this equation. dp by dt, as we pronounce it, equals p times t, big T, where p is population, big T is technology, and little t is time. Now, to be fair, they had a slightly different version of it using n instead of p, for example, but this is the version we'll be using in this course. And from this equation, all sorts of interesting things follow, and that is what Korotayev and co. wrote up in their books on macrodynamics. Now, this thing is a derivative, and it represents the rate of change of population with time. And this whole equation is a differential equation. And derivatives and differential equations are the subject of the mathematical topic of calculus. And that is what this lesson is about. So it's to help us understand what an equation like this means and what we can do with it. And in this first part of the lesson, I'm going to concentrate on this idea of the derivative, to understand where it comes from and what it means. So suppose we're interested in the growth of world population, and we want to study how the population was changing, the rate at which population was changing over time. So I put up here a table with the time and the population at each time. And I'm measuring the time in millennia, so 0 up to 10 millennia. And the population is measured in millions. So we go 0, 1, 4, 9 up to 100. And now you might say, well, you know, if you start with a population of 0, your population is not going to grow. So just imagine this is Adam and Eve, 2 people. So when we're measuring it in millions, that will be 0.00002 million. So it's, as you know, it's close to 0. It's 0 to the nearest million. So that's what that means. And what we want to work out is the rate of change of population. So to do that, we can firstly work out the change of population at each step. So for this first point here, it went from 0 to 1. So the change in population was 1. And then at the next step, the population increased from 1 to 4 million. So the increase was 3 million. And then from 4 to 9, 5 million. And I'll fill in the rest. Now, this change in population, what we're doing is finding the differences at each time step between one time step and the next. So from 0 to 1, the difference is 1. From 1 to 4, the difference is 3. So we write that as delta P, where delta is the 4th letter of the Greek alphabet, and it's the letter D in the Greek alphabet, so D for delta. So delta just means standing for difference, as D for difference, delta for difference. It's the difference in the population, delta P, and that is also measured in millions of people. Now, that's the change in the population, that's the increase in the population, but it's not the rate of increase. We want the rate of increase. So to find the rate of increase, we need to divide by the time taken for the increase. So the time taken, we can say, is the difference in the time, at each step. So we can write that as delta T, and that will also be in millennia. Now, this is pretty easy because of the way I've constructed the table. I'm counting millennia at each, 1, 2, 3, 4. So the difference is always 1. So delta T is just 1 in each case. And then lastly, what we're interested in is the rate of change of population. So that is delta P divided by delta T. and that is measured in millions of people per millennium. So to do that, we're going to divide delta P by delta T. Well, again, it's very easy because all our delta T's are just 1. So 1 divided by 1 becomes 1, 3 divided by 1 becomes 3, and so on. Now, although these numbers are the same, they're conceptually different. So it's like if I said you went on a journey of 30 miles. 30 miles is the distance you travelled, it's not your speed. If I told you that the journey took an hour, then you could work out your speed. It was 30 miles per hour, 30 miles in 1 hour. So although it comes to the same number, 30, 30 miles is the distance and 30 miles per hour is the speed. And so if I'd said that your journey was 60 miles and it took you 2 hours, then you would still calculate that your speed was 30 miles per hour. So, because it's 60 miles in 2 hours, 60 divided by 2 is 30 miles per hour. So in that case, the numbers don't come out the same. So although here they do come out the same, they are conceptually different. This is the rate of change and this is the absolute or actual change. And in finding this rate of change, what we've done is we've found the differences between the successive values. So when it went from 1 to 4, the difference was 3. 4 to 9, the difference was 5. So, and that's why we called it delta P, delta for difference. And so this is called differentiation. We have taken differences, differentiation. And this thing, delta P, the difference, is also sometimes known as the differential. And this delta P over delta T is sometimes also called the differential, but more strictly we'll call it the derivative. So this is the derivative, it's the rate of change of population, which we have derived using this table, finding the differences, differentiation, giving us the derivative. Now, you probably noticed that the population figures here are just the square of the time. So when it's 4, 16, 5, 25. So we can actually write down a formula for what the population is at any time. The population is just equal to the square of the time. P equals T squared. Now, when I write P, P is not actually just a single number. It's a whole set of numbers. And the actual value of P depends on what time you're thinking about. So a way of representing that is to write P as P of T. You sometimes pronounce it. P as a function of time. P at time T, we might say. Or P at T, something like that. All those things mean the same. But what we're saying is that P depends on the time. So we've strictly got it's P of T equals T squared. P is a function of time, and this is the specific function we're talking about, the square. Now, although we can write it that way, we might imagine, Einstein's famous equation, writing it this way. E of m equals mc squared, because the equation is telling us that energy is a function of mass. Energy depends on mass. So strictly we should perhaps write E of m, energy is a function of mass. But of course that's not really a very neat way of putting it. It looks a lot better like that. And the dependency on m is implicit in the equation. The equation is telling us that energy is depending on mass, so we don't really need to make that explicit by putting that bracket m after it. And in general, we'll just write equations like P equals T squared. But the reason we might put P of T is when we are saying that we're wanting to emphasize that P depends on T, though we don't actually know what that dependency is yet. So we're just pointing out that it does depend on t. It might be, you know, I'm telling you that p depends on t, and I'm now about to derive what that dependency is. We can also write this in different ways. Sometimes people might write a subscript t, pt. That also means p at time t. And saying that p is a function of t, also we saw in the last lesson, we can write that p squiggle t. That means p varies with t, p depends on t, p is a function of t. All those things mean much the same. Now the reason I brought that in is because we're going to use it in the next step, use this idea of just writing something as p of t. So going back to this, we said p equals t squared. The population is the square of the time. Can we find a formula for delta p over delta t, the rate of change of population? Well, I hope you can see that yes, we can find a formula. It's just 2t plus 1. When t is 0, 2 times 0 plus 1 is 1. When t is 1, it's 2 times 1, which is 2, plus 1, which is 3. 2 times 2 plus 1 is 5. 2 times 3 plus 1 is 7. So with p equals t squared, we're finding that the rate of change of population, delta p by delta t, is equal to 2t plus 1. And we could have predicted that, because we know that p equals t squared, and we know that this delta p is the difference between one time step and the next. So we could actually calculate what delta p would be. It's going to be the population at time t plus 1 minus the population at time t. That's how much the population increases in one time step between t and the next time step, which is t plus 1. And using this p equals t squared, then the p of t plus 1 is going to be t plus 1 squared minus the population at time t is t squared. And then t plus 1 squared, we can, using our basic mathematics, multiply out the bracket, and that gives us t squared plus 2t plus 1, and then minus t squared. And the t squareds here cancel, and we're just left with 2t plus 1. And then that's delta p. Remember, we want to find the rate of change of population, delta p by delta t. So that is 2t plus 1 over, our delta t's were 1, always 1. So it's, of course, just comes back to 2t plus 1. So the rate of change of population, if p is t squared, comes out as 2t plus 1. Now I want to look at this in a slightly different way for a moment. Okay, so what I've done is plotted the population p against the time t. So at t equals 1, the population was 1. At time 2, the population was 4. Time 3, the population was 9. And when we're talking about delta t, we're talking about this distance along here. Delta t is the change in the time. It's the time step. So that's delta t along there. And when we're talking about delta p, we're talking about the change in the population. So it's the increase in population going up here. It's this length here, the change from 1 to 4. And so when we're talking about delta P by delta T, we're talking about the increase in the height divided by the increase in the distance. And that is the slope of this line. That's the definition of the slope. It's how much you go up for each step along. And if you go up a large amount in a step, then you've got a steep slope, a large slope, and if you go up a small amount for each step along, you've got a small slope, a shallow slope. So delta P over delta T corresponds to the slope of this line. Now, I said though that the population P equals T squared. And so population is constantly changing as time is changing. I've just shown it at these points, particular points of 1, 2 and 3, but P will be equal to T squared between these points as well. And it's actually going to be a curve of P equals T squared, looking like something like that. And when we measure this slope here, we're measuring the average slope over this time step, but it's not exactly the slope at this point 1 here. We said it was. At point 1 we said this slope was 3, but actually that's 3 is just the average slope. It's the slope of this straight line, which is not the same as the slope of the curve of population equals T squared. Because if we look here, I haven't drawn it very well I'm afraid, but if you look here, the slope there is a bit shallower than that slope, whereas here it's a bit steeper. If I could draw it, it's increasing faster than that average slope, whereas here it's increasing more slowly than that average slope. And then the average of the two, or the average over that whole time step, comes out to that. So our calculation here of the rate of change of population at each time step is only a rough estimate. It's this average. If we want to get a better estimate, we should take a smaller time step here and just go along a short way, and then we'll be sticking closer to the actual curve, the P equals T squared curve. So let's say we'll take that as a time step, not of 1, but 0.1 millennia, which is in other words 100 years. And when we take a small time step, a small step, we use the lowercase Greek letter delta, so small delta t. So when we use a small delta or lowercase delta, it means, our time step is small. If it's a capital delta, it just means a change of any size, a macroscopic large change. But delta t means we're taking a deliberately small change. And correspondingly, we're going to have a small change in the population, which we'll write as delta p. So given now then this small time step, we can work out again what we would expect our delta p with small time steps to be. And this will give us a more accurate estimate of the actual rate of change at this point, the actual slope of the curve at that point. So we'll take delta p to start with. So let's in fact we're going to work out delta p over delta t. So we'll start by finding delta p. Well, delta p is going to be the population now at time t plus 0.1 minus the population at time t. We're now just stepping forward 0.1 of a millennium. And then just following through exactly the same as before, this is t plus 0.1 squared minus t squared, which is t squared plus 0.2t plus 0.01 minus t squared, which is equal to 0.2t plus 0.01. And lastly, we want delta p divided by delta t. So that's going to be (0.2t plus 0.01) divided by delta t is now 0.1, not 1. And that gives us 2t plus 0.1. 0.2 divided by 0.1 is 2, and 0.01 divided by 0.1 is 0.1. So we've now got this better estimate for the slope, the rate of change. It's delta p over delta t is 2t plus 0.1. So when we calculated, for example, the rate of change at this time step 1, before we had 2t plus 1 and it came to be 3. But we now know that a more accurate figure would be here actually 2.1. And so this is a better estimate, but it's not the best estimate we could get. We could do all this again using a time step of 0.001, which would be even better. So we can rewrite all this. This is going to be p of t plus 0.01 minus p of t now, which is t plus 0.01 squared minus t squared, which is t squared plus 0.02t plus 0.0001 minus t squared, which is just 0.02t plus 0.0001, and then we're going to divide that by our delta t, which is now 0.01, and this will come to 2t plus 0.01. 0.01 into 0.02 is 2, and 0.01 into that is 0.01. So an even better estimate would be 2.01. If t is 1, 2 plus 0.01, 2.01. So the smaller our delta t, the better the estimate we're getting. And as you can see, it seems to be getting closer to 2. And indeed, we'll show that that is the case. So let's do this now, not taking a specific delta t, but let's just take a general delta t and see what happens. So we're going to calculate delta p by delta t without saying what delta t is in advance. So that is going to be now, taking delta p, it's the p of t plus delta t minus the p of t. So we know how to do all this now. Squared minus t squared, which is t squared plus 2 delta t minus, plus delta t squared minus t squared, so that's just 2 delta t that should be a t there as well, delta t times t, I'll put that, plus delta t squared. So delta t, that's delta t times t. And then delta p over delta t is going to be, divide this by delta t, so that delta t cancels, we're just left with 2t, and delta t squared divided by delta t, we're left with just delta t. And so the smaller delta t, the better our estimate of the slope. And so let's take the smallest possible delta t, which is just 0. So we can let delta t be 0. Now, strictly in mathematics, we say we don't let delta t be 0 because that would mean dividing this by 0. And as we know, in mathematics, dividing by 0 is a big no-no. So strictly speaking, we don't take it to be 0. We take it to be infinitesimally small, an infinitesimal. And an infinitesimal we write as dt and dp. So when we let this be, if delta t is 0, we write it as dt. But as I said, we don't, strictly speaking, it's not 0, it's infinitesimally small, but it's, as far as we're concerned, it's 0. So if we're going to use dt and dp with this infinitely small dt or 0 dt, then we're just going to get dp by dt equals 2t, because that dt means delta t is 0. And so that is a formula then now for the derivative that is exact. And this dp is the exact differential with a d in front of it. So what we can say, if p equals t squared, we now know that the derivative dp by dt equals 2t. And conversely, if somebody told you that the derivative was 2t, we would know that the population is given by p equals t squared. So we're now doing calculus. Given a formula for a variable, we can work out its derivative, its rate of change. And we can, of course, only do this in this one special case of t squared at the moment, but in the rest of this lesson, we will go through a whole range of functions and what their derivatives are. And we don't need to do this whole laborious process for each one. We'll just go straight to what the derivatives are. And there are some simple rules to how to find derivatives that we then just need to memorize. Okay, now put up another imaginary example here, showing how the population of a city, P, depends upon its area, A. So the area is measured in square miles and the population in millions. So when the area is 10 square miles, the population is 2 million, let's say. And the point of this is that when we're finding derivatives, it's not necessarily just with respect to time. It's not just the time derivative. We could also have the derivative here of the city population with respect to area. So it's how fast the population changes for a given change in area. So just as we had with the time, we can have delta P divided by delta A, the change in population divided by the change in area. So, from here, the delta P is 2 million, corresponds to a change in area, delta A, of 10, from 10 to 20. And similarly, we could think about, taking smaller steps. So we could write as delta P over delta A, or if we had an exact formula for the population as a function of A, then we could find the exact derivative dp by dA. So the point of this is to say, just to emphasize that derivatives can be with respect to any variable, not just with respect to time. And I'll take another simple example. Let's suppose we're interested in the relationship between the per capita crime rate in a city and its population. And let's suppose we believe that it is proportional to the square of the population. And we might say that because the per capita crime rate depends upon the number of potential victims and the number of potential criminals. And the number of potential victims is just the population of the city. Everybody's a potential victim. And the number of potential criminals is also just the population of the city. Everybody's a potential criminal. So we just multiply the two together and giving p squared. So the per capita crime rate is equal to p squared, we might say. Again, just an imaginary example. But given this, then we know that the rate of increase of the per capita crime rate with population size is equal to p squared. Well, it's going to be 2p, just the same as when it was t squared and we differentiated with respect to time, we got 2t. So if we've got p squared and we differentiate with respect to p, we'll get 2p. So this is telling us that the per capita crime rate increases with population at a rate that depends upon the size of the city, the population size of the city. So if we add a certain number of immigrants to a large city, there'll be a greater increase in per capita crime per person added than in a smaller city, because a larger population will mean that the per capita crime rate is increasing more quickly with each person we add. Again, just an imaginary example, but to show the kind of ways in which we might use these ideas of derivatives. And now I'll put it in a more abstract way. We can say, suppose y equals x squared, so we'll use more abstract variables of just y and x, which could be any variables. Then dy by dx equals 2x. And thinking about the idea of functions, when we write here that y equals x squared, just going back to something I was talking about earlier, we can also say that y equals y of x. That is saying that y depends upon x. Or we could say that y equals a function of x, f of x, because f of x itself implies a function of x. So y is a function of x. Those are other things that we might say. And now I'm going to talk through a couple of other little points about how to work with derivatives. So the first one is, if we've got dy by dx, then what is dx by dy? If we've been told dy by dx, how do we work out dx by dy? Well, as we know, this dy by dx came from fractions. It was started off as delta y divided by delta x. And this isn't strictly a fraction, because this dx, remember, is infinitesimally small, or effectively 0, and we can't really divide by 0. So this isn't really properly a fraction. But nevertheless, they behave like fractions, and for our purposes we can treat them as fractions, even though mathematical purists might not approve of that, but it works for reasons that could be proved rigorously. So if we've got dy by dx, then we want dx by dy, we just turn the fraction upside down, so we just take the reciprocal of it. So dx by dy will just be 1 divided by dy by dx, or it's 1 over dy by dx. And we could see that with our example of the city areas and populations, that we've got 10, 20, 30, 2, 4, 6. If we're finding dp by dA, the population increases by 2, the area increases by 10. So dp by dA is 2/10, or in other words 0.2, and dA by dP, how much does the area change for a given increase in population? Well, it's clearly just the other way around. The area increases by 10 when the population increases by 2. So that's 5. So dA by dP is 1 over dP by dA, as 5 is 1 over 0.2, and 1 over 5 is 0.2, and 1 over 0.2 is 5. And the next one we'll consider is very important. It's known as the chain rule. Which says that dy by dx is equal to dy by dz times dz by dx. So again, they're working like fractions. The dz on the top and the dz on the bottom cancel out, and we just get dy by dx. So this is useful in situations where we're not told dy by dx directly, but we do know how y depends on z, and we do know how dz depends on dx, on x. So it might be, for example, that we want to find the rate with which the city population is changing over time. Well, we've been given how the population changes with the area of the city. We were just looking at that. And we've also been told how fast the city is growing in terms of area, in terms of square miles, dA by dt. And so we can multiply those two together to get the rate of change of population. So we know, as we've just seen, that dP by dA was 0.2. So if we're told that the city is growing at the rate of 0.1 square miles per year, let's say, then we multiply those two together. 0.2 times 0.1 gives 0.02, and that's the rate of change of the population in millions of people per year. And this rule in general is very useful in finding calculus formulas, as we will see. And the next important point is about what is known as the second derivative. So I've just drawn up a little bit of our original table of world population over time, and we calculated this rate of change of population, which was dP by dt, but let's just write that as, let's just assume it's the exact derivative, and we'll call that dP by dt. Well, that was increasing itself. Here the rate of change of population was 1, but sometime later the population was increasing at the rate of 7 million persons per millennium. So the rate of change of population is itself increasing, it's speeding up. So we might want to find the rate of change of the rate of change of population. So to do that, we are going to consider the d of dP by dt dt. So just as we found the rate of change of population by doing dP by dt, if we want to find the rate of change of that thing, we do d of that by dt. Well, we can treat this as a fraction. It's like d over dt times dP over dt. And so we've got d times dP on the top, which gives us d2p. We write it as d squared, but we pronounce it as d2p. So there's d times d squared p, d2p, over dt times dt, dt, and this time we do say squared. So the second derivative, the rate of change of the rate of change, is d2 by dt squared of whatever the variable is, or it could be d2p by dA squared, whatever. But the second derivative is d2 by d something squared.
This is just explaining the notation for the second derivative. It is not about how we actually calculate it.
And then we can imagine the nth derivative, because we could differentiate that again, and the nth derivative would be dnp by dt to the n. So if we know what dp by dt is, and we take the derivative of that, we write that as d2p by dt squared. And if we keep doing that, we're looking at dnp by dt to the n. And lastly, I'm going to mention a special notation that is sometimes used. So we know that if we have a function y, we can express its rate of change with respect to time as dy by dt, and also the acceleration, the rate of change, or the rate of change is d2y by dt squared, and we could go up to higher derivatives as well. Well, we can also write this as, starting with y, the derivative with respect to time as y dot, and the second derivative with respect to time as y double dot, and so on, 3 dots, etc. And all this is just a simplified or shorter way of writing the same thing. Instead of laboriously writing out dy by dt, we just write y dot and y double dot. And this is only used when we're differentiating with respect to time. So if we see a dot, it always means with respect to time. But we know that we can also differentiate with respect to other variables. So we could have y and then dy by dx and d2y by dx squared, and so on. And in this case, we have the shorthand notation writing y and y dash, and d2y by dx squared we write as y double dash, and so on, triple dash, etc. Or some people say prime, so this would be y prime, y double prime. And again, this is simply a shorter way of writing the same thing. It's just to save, effort. And we'll sometimes use that where, it's helpful. And I've perhaps mentioned that this way of writing things out is known as the Leibniz notation, after Leibniz, who developed it. And this is Newton's preferred method. Leibniz kind of won out as this being the sort of main standard way of writing derivatives, because it's more intuitive. Things like the chain rule, for example, really stand out when you use this notation, because they look like fractions and they function like fractions, and we can see how things cancel. But still, Newton's approach is a lot quicker to write, and in certain circumstances we will certainly use that.